So, hi, my name is Michal. I'll be talking about sampling algorithms for determinantal point processes. This is joint work with Daniele Calandriello and Michal Valko. And there's a paper online with the same title, if you are interested. OK, so I'll start with some motivation and some background. Some of you probably haven't heard of determinantal point processes, so that'll be useful. OK, so the basic sort of task we're concerned with here is finding small representative samples. So how can we select small representative samples of data? Interesting. You can try to select uniform samples. You can try to select IID, select them by IID importance sampling. But what about the birthday paradox? So what does that have to do with anything? So the birthday paradox says in a room of just 23 people, there's a 50-50 chance of at least 2 people having the same birthday. So this is just a special kind of example that if we draw a uniform sample, there's a very good chance that there will be some element of that sample that is completely redundant. Of course, this is an extreme case, but and sometimes we sort of care about having every single point be kind of adding more information about our data. So as an example of this, you can look at search and recommendation. For example, if we want to Google something, we Google, let's say, image search for neural networks. We have a bunch of images. We don't really want, or we don't want, and Google doesn't want to show us 2 virtually identical images. It's redundant. They could have put an ad there and made some money. So it's not great for them. It's not good for us. And of course, this is a corner case of something more broader, which is that we want the sets of samples to be diverse, right? So it turns out one way to capture diversity that has been recently studied in the machine learning literature in particular is determinantal point processes. So let's just jump into a definition here. So we are given, so we define a determinantal point process via a PSD matrix L. So it's an n by n matrix, and this defines a distribution over subsets of items from 1 to n. Right, and the distribution is defined as follows. The probability of a subset is proportional to the determinant of the submatrix indexed by that subset of the submatrix LS, right? Indexed by the subsets with both rows and columns being indexed by S. Just one peculiarity about this definition is that we're selecting subsets. We're sort of sampling over subsets of all possible sizes, so all subsets of 1 to n. But generally, that's not really a problem. The distribution ends up being highly concentrated on particular subset size that we can easily sort of choose. So the nice and sort of very unique thing about this distribution is that even though we're not sampling independently, we're sampling from this combinatorial sort of object, the distribution has a closed form normalization constant. So there's this constant in blue, which is also a determinant. And if we really want to sample a subset of a fixed size, we can do that. Those are called k-DPPs. So we just take a DPP and we condition on a subset size being k. And then we sacrifice the nice closed form normalization constant in that case. So DPPs have actually been used and observed in many sort of fields, including random matrix theory, graph theory, have been used in optimization more recently, and also randomized linear algebra. I'll talk about that a little more in a moment. and also, as I mentioned, in machine learning and recommender systems as well. Okay, so why does this? Why would this distribution induce diversity? So for this, we go to the sort of formulation of a determinant as volume. So suppose that our matrix L is a kernel, sort of a kernel matrix of dot products between n vectors in some Euclidean space, as it says here. So then the determinant of the submatrix Ls for any subset S corresponds to the volume squared of the parallel pipette spanned by the vectors that we select, right? So volume has this property that it induces diversity in the sense that well, we're not going to have two vectors that are really close to each other in the same set, because that will have very low probability. And it also sort of promotes vectors of larger length. So it works at the same time as a sort of an importance sampling distribution as well as a diversity-inducing distribution. Any questions so far?
If two vectors just are exactly opposite, then that means.
Right. So I mean, yes. So if so it measures. So volume measures a certain kind of diversity, right? So yeah. So if you wanted to say have vectors that are kind of in opposite directions but kind of collinear to be likely to be sampled, you could, for example, I mean, basically you can sort of choose the notion of metric space in which you're going to compute your volume. You can design it the way you want it. So this is one way you can do it. Another way is you can replace this dot product with whatever kernelized dot product you choose. For example, like RBF kernel, if you're familiar with that. And then, for example, then the notion of diversity would just be based on distance, and then vectors in opposite directions would be diverse in that sense, right? So you can sort of adjust the notion of diversity as you choose. Okay, so as an example application, as sort of one last motivation for talking about DPPs, I'll talk about a task which I think should be most familiar to this audience, which is column subset selection. So this problem is as follows. We have n vectors in 2 dimensions. We want to select a small subset to minimize the following quantity over there, which basically, so this already appeared in some of the talks. Basically, we want to look at the subspace spanned by the subset of the vectors, and we want to measure how well the subspace matches with the whole set of vectors, in the sense that the error here is the error of the projection of all the data points onto that subspace. And just on the side, there's also a variant of this problem in the kernel setting, where instead of giving us the n vectors, we can also be given the matrix L directly, the matrix of the dot products. And in this case, this is often referred to as the Nystrom method. And both of these problems, there's sort of a lot of literature on the topic from both machine learning and sort of computer science communities. And so here's a result that makes DPPs relevant in this context. Specifically, well, let's just parse this really quickly. We obtain that if we sample from a particular fixed size DPP, then we can show that the sort of expected error of the subspace chosen this way is bounded in terms of, so this right-hand side is the sort of the best possible subspace we could find, which corresponds to, for this problem, for this error, corresponds to the picking the subspace of the first k singular vectors of the data set. And the reason that this bound is interesting is that it is actually shown to be essentially optimal. It's tight in a very strong sense up to lower order terms. So the first version of the bound was shown by Deshpande, Rademacher, Vempal, and Wang, and there was a further improvement by Guruswamy and Sinop. There has been other approaches have been proposed for this specific problem, but the DPPs essentially get the tightest sort of possible bound. And just a minor side note here, there's a k and an r. So we wanted to pick a subset of size k, and then the bound gives you, so that would be the choosing r equals 0. So there's I allowed here to give you a certain slack and pick a subset of a size k plus r. This is a sort of a minor element, but if we want to,
that's an equality if r is 0.
If r is 0, that is not an equality, but well, it can be an equality for certain data sets. Actually, no, that's not entirely true. But it can be made arbitrarily close to an equality, I guess, which is what makes the bound tight. But it's not actually an equality, no. So yeah, so if we pick r larger than 0, then the bound improves, and we can get a 1 plus epsilon multiplicative approximation. Yes?
Are there known relationships between the optimizers of these problems, like the minimizer of this column subset selection versus like the maximizer of the volume maximization problem?
It's not that you can just, so when you're sampling from the DPP, you're not really choosing the maximum volume subset, right? You're just sampling, right? So I don't think picking the maximum volume subset would necessarily get this bound. So it's kind of, it seems like you need the sampling to do this, as far as I know. I mean, so I don't know any specific relationship. People also, there's a lot of work on maximizing the volume as well, on maximizing the determinant, so finding the mode of the distribution. But that's not exactly what we're talking about here. OK, so this is an example of a sort of a theoretical motivation for DPPs, and people also use them in practice in various settings. All right, so let's talk about the algorithmic challenges for sampling DPPs. So the task, as we're going to define it, is very simple to define, right? We're given, in some form, we're given the matrix L. We want to sample from DPP of L. That's it. Another variant might be that we're given L and K. We want to sample from the k-DPP. And as we've seen, another interesting variant is if we're given not L explicitly, but rather the n vectors. That's something we've also considered. So I hope that the basic task is clear. So what are the challenges? So the basic costs involved in sampling DPPs is that generally there's going to be some preprocessing cost. We're going to have to look at matrix L and get some information out of it. Generally, for most algorithms, this involves some kind of an eigendecomposition step.
Why do you need the eigenvalue?
I actually will talk about it in a moment. So there's a specific algorithm for DPPs which uses eigenvalues and eigenvectors.
I thought that the Poleski factorization might be more.
There is another algorithm that uses that as well. I'll not have a chance to discuss it, but the most classical algorithm uses the eigendecomposition. And so once we are over this step, then things get somewhat better, and then there's like a sampling procedure typically, but that still is often somewhat expensive. For example, it often requires to do a pass over all of the data, so it scales linearly with n usually, which is already often too expensive if we want to sample repeatedly for our task, which is often the case.
Sorry, so for any k, you are saying you can sample, mixing time for one sample is n, linear in n?
At the moment, I'm not making any such statements here. This is just a kind of high level. There's many, many algorithms, and I'm just kind of trying to boil them down into the key bottlenecks here. But for now, I'm just saying generally the sampling time at least scales with n.
At least.
At least with n. Unlike, for example, if you would compare to, say, IID sampling, there's some initial cost, but then sampling is very cheap, right? Here, there's some initial cost, but then sampling is still pretty expensive. This is finicky. OK, so now, finally, as there has been a lot of literature trying to overcome these issues, people have run into basically a trade-off between accuracy and runtime, in that many exact algorithms that have been proposed, well, they require some form of either eigendecomposition or some kind of decomposition of the matrix L, whereas there have been many, many approximate algorithms that try to avoid exact decomposition. But then it's very difficult to get approximation guarantees in theory, and it's very difficult to evaluate that the sampling algorithm we have actually, that it has some, whether or not it actually is sampling from a good approximation. So there's a lot of heuristics in particular. OK, so let's look at a few examples of related work. So the main one is an exact DPP sampling algorithm, which is based on a result of Hugh, Krishnapur, Perez, and Virag from 2006. This is a very nice result, sort of a seminal work in this topic. I will not have a chance to discuss it in proper detail. Essentially, it shows that any DPP can be decomposed as a mixture of quote-unquote low-rank DPPs, which are called projection DPPs. So I will not get into that. But essentially, what that means is, and here is where the eigendecomposition comes in. So if you are given an eigendecomposition of the kernel matrix, then you're sort of able to, every time you sample, you are able to reduce the problem to a low-rank instance of the problem, which is easier to solve on a high level. That's what's going on. I refer to the papers. And so that means that the cost of the first sample we're going to obtain from this procedure is going to be the cost of the eigendecomposition, so it's going to be expensive. The cost of every next sample, if we're interested in more samples, is going to be cheaper but still grow linearly with n. So k here, generally k is going to denote the expected subset size or the exact subset size. And this also extends to k-DPPs. So basically, our results are also going to be framed in the following fashion, where we're going to try to improve on both the first sample cost and the second sample cost. So is this clear?
So by exact, you mean the probabilities are exactly right?
Yes. Yeah.
So Markov chain wouldn't do that?
Markov chain wouldn't do that. And thank you for bringing up Markov chain, because this is the second related work. So yeah, Markov chain wouldn't do exactly that, but there's some very nice result by Anari, Garan, and Rezai from 2016, which says that the very basic MCMC chain for a k-DPP that you can think of, which just picks an arbitrary subset of a particular size, and then picks one point from within and from outside of the subset randomly, and then decides whether or not to swap them or not. And that decision is made with the appropriate probability. So this is the most basic MCMC algorithm for this problem you could think of. Turns out this actually has a rapid mixing time. And that, in fact, completely avoids eigendecomposition, which is very nice. But the sampling cost still is somewhat expensive. So every time you get a sample, the cost is order n times poly k, some polynomial in k. So in fact, the getting of every next sample might be actually slower than the previous algorithm. And this also extends to DPPs where the size is not fixed, with some trade-offs. And also, this is approximate.
What's the poly k? It's n times k times maybe a k cubed or something. You have to do this as
It's not
at each step, or what's?
It's like maybe k cubed or something like that. It's not outrageous.
Because the thing you have to do at each step to evaluate that metropolis filter factor.
Yes, you have. I mean, at each step you have to compute the determinant basically, or update the determinant that you're computing, basically. Yeah.
So shouldn't there be at least n log n, because coupon collectors has to come in somewhere.
Yeah. Sorry. The
log factors.
The log factors. I'm being sort of sloppy about the log factors here.
And you don't have no assumption on relative lengths of the columns or rows of L and things like that.
No. Here there's no such assumptions. Right. So there's a number of other works.
No, but L is square, right?
Sorry?
L is square. It's only x that may be long, but L is size n, right?
L is n by n.
Yeah. So
I mean, what do you mean there's no factor depending on n? N is one of the factors.
no, depending on the lengths of rows.
But
Oh,
the
you mean
x
norms.
could be,
Yeah.
the x's could be longer.
There's a lot of disparate norms.
Right.
Anyway,
You could have that. Yes, no problem. I mean the fact that the mixing time C depends on n, which means that in some sense you will have to eventually see every single row at least once to start converging, right? So that's, yeah.
Is uniformly sampling, you know.
Yeah.
You may be able to come up with a better trial by looking at something like
Right.
that.
Yeah, so there's a number of other works. I cannot review them all, but essentially a lot of them are various heuristics trying to avoid eigendecomposition and give some kind of a guarantee on the approximation quality, but that generally requires various assumptions. Okay, so let's go into the main results. Right, so the main result I will be talking about is a new exact DPP sampler. And all right, so let's just parse the statement. So there's an algorithm which, given access, sort of entry access to the matrix L, returns a sample, an exact sample from the distribution, from the DPP of L distribution, in time n times poly k times poly log n. And if we want more than one sample from the same distribution, then the next sample can be obtained in poly k time. I can give all the polys at some point later. Okay, so let's look at what's sort of interesting about this result. First of all, we're sampling exactly, right? And the cost of the first sample is possibly less than the exact eigendecomposition. And in fact, it is sublinear in the size of L. So we didn't actually have to see all of the entries of the matrix L, and yet we are sampling exactly. So this is somewhat analogous, to a certain extent, this is somewhat analogous to results which talk about approximating PSD matrices in sublinear time, except sort of the cool thing here is that we're not doing any approximating. I mean, under the hood, we will be doing approximating, but in the end, we get we return the exact answer that we wanted to return.
So you don't have to see even all the entries. L might have only one non-zero entry out of the n squared. How do you get to see that in time n?
Well, L has to be PSD matrix, which introduces some constraints, as we know,
Okay.
but you don't have to see all the entries, no. And finally, the actual sampling cost. So essentially, you can look at this result this way: as the first line is the cost, or the 0.1 line is the cost of preprocessing, whereas the number 2 line is the cost of the sampling. So the cost of the sampling is completely independent of the size of L. What it actually depends on is the size of the sample we're going to get, so the subset. And so this we can extend this to also fixed size DPPs, so the k-DPPs as well. So the same statement holds if we just replace it with k.
Isn't this for k-DPP? What else is the k then in
Right, good question. So k here, earlier I kind of mentioned that I will use k to either denote the expected subset size or the exact subset size. So here k means the expected subset size of S drawn from DPP of L. And it's generally assumed to be small. Basically, whenever you actually want to sample from a DPP, the size of the subset you want to sample is going to be much, much smaller than n. But if you want to enforce the subset size, you can do that. And by the way, the setting where we are given the vectors xi explicitly is actually easier. I have a paper on that. There was actually a precursor to this paper. So we can handle that setting as well. And the runtimes are, I mean, different, but kind of as you would expect them to be. So the input sparsity time type guarantees are possible there. All right, so a quick comparison of the algorithms that I mentioned with our result at the bottom. So then we have here, two time complexity columns. So the things to point out are that for the first sample time complexity, our algorithm is the only exact algorithm that goes below eigendecomposition cost. And for the next sample complexity, it's the only one that does not depend on n at all.
So that means you don't have to see all n squared elements of the matrix?
That's right.
I think the question was asked already, so I guess it's just surprising.
It is surprising, I agree. I mean, I would say given prior work, it's not necessarily surprising that you can sample approximately, but the fact that you can sample exactly is still somewhat surprising to me. I think I'll try to shed some light on that in the talk.
But even for a positive semi-definite matrix, you could have very small diagonal entries, all of them except one.
I mean, if it's just the diagonal entries, you can see the diagonal entries, right? Because there are just n of them, right? Yeah. So.
So you're describing this in terms of DPPs, and then as sort of a side, you're saying you could run this metropolis algorithm, or the Markov chain.
Mm-hmm.
The metropolis won't give you exact.
No, it won't give you exact. But if you were to come from the other perspective and say, I want to estimate something, maybe approximately, the obvious thing is to run a Markov chain, and you get something approximate. And then there's, in the big universe of Markov chains, there's a little bit of work on sort of exact samplers, where you get, I think it's Wilson, and is it Prop and Wilson, or do you remember what? Is there, and is this a special case of that because you can evaluate the partition function exactly, or do you have any idea?
It's, I'm vaguely aware of this. As far as I know, there's no exact sampler of of MCMC type for DPPs, and this is also not one of them. So this sort of behaves using a different sort of paradigm. All right, so so the time complexities are one thing, but we actually implemented this. It runs in practice. We're putting the code online and so forth, and the sort of the tagline of the experiments is that we can, for the first time, run DPP on the whole MNIST data set, which for the ML people is an accomplishment, I guess. But yeah, the bottom line is, I mean, the runtimes confirm the time complexities, I guess, and we're faster and so forth. All right, so let's talk about the sort of the technical aspect of the result. So the key sort of concept we're going to use is the idea of distortion-free intermediate sampling. So this is a sort of a meta strategy that is not specific to DPPs, and I actually first developed this earlier in an earlier paper for some special case of those so-called projection DPPs with Varmut and Su. And so here's the idea. The idea is very simple. And I mean, as it's stated here, kind of at the moment, maybe not specific, but the idea is to take the entire data set and downsample it to the intermediate sample, which we call here sigma, right? So sigma 1 to sigma t, those are t items from our data set. T is much larger or somewhat larger than the target subset size. And then we're going to downsample from the sample of size t. So we're going to sample from that sample, and we're going to return only the elements selected at the end, right? So there's sort of a two-stage process, right? So what we want is that the sigma be a distortion-free intermediate sample, which means that we have to have a way, in point 2, we have to have a way to sample out of sigma in such a way that that the end result, the sigma I for INS, is distributed according to the original distribution over the whole data set. So here, sigma is not something that we construct and then keep fixed. Sigma is a random variable. So it's the randomness of sigma is part of the randomness of the whole algorithm, which makes it possible to get the exact sampling.
I'm sorry, so you have a set, you pick a smaller set, from a smaller set you pick a smaller set. So how does that relate to determinants?
It does not at all. That's my point is this is a meta strategy that could be applied to any other sort of sampling distribution, but it really only makes sense if your sampling distribution somehow is combinatorial in nature. Otherwise, it would probably not be very useful. But yes, it's more general than the determinants, right? But they will, of course, come shortly. All right, so how to choose the intermediate distribution? Well, of course, the goals are, first of all, it has to be efficient. And second of all, it has to have this property that it's distortion-free.
Sorry, why don't you just choose the small one right away? Why do you have the intermediate one?
OK, so imagine that we have we are given some algorithm for sampling from our target distribution, the DPP. And it's an expensive algorithm, right? So let's say it's the n-cubed algorithm. So if we run the n-cubed algorithm on the whole data set, it's going to take n-cubed. Whereas if we run it only on the downsampled data set of size t, it's going to only be t-cubed.
But it may not give you the probabilities you would have got if you had done it on the original matrix.
But it turns out it will.
OK, and show us.
Exactly. All right, so how do we, yeah, I hope I don't run out of time before. All right, so we want efficient and distortion-free.
Well, the idea is efficient means the first step's efficient. Distortion-free means you can chain these things together, but you also want the second step to be efficient. So efficient means two things, right? Efficient
means that the intermediate distribution is efficient. The second step is just going to be the expensive algorithm done on a smaller.
Because you state it as an existential result, so it's the obvious algorithm done on this.
Does it have to do with the Cauchy interlace theorem for the eigenvalues, the fact that they're interlaced?
It does not, no. All right. So I was going to, all right. Well, what's the intermediate distribution? Well, surprise, surprise, it's levered score sampling. It's actually ridge levered score sampling. So, I mean, I think we're all familiar with the definitions of ridge levered score sampling and the effective dimension at this point. So this is how you sample according to sample IID according to ridge levered scores. And so why is this a natural candidate for the intermediate distribution? So two key properties it's good to keep in mind is that the marginal probability of a particular point being in a set S for a DPP is exactly its ridge levered score with lambda equal 1. And from that, it immediately follows that the expected subset size of a DPP is the effective dimension for lambda equal 1. So there's a very close connection generally between DPPs and levered score sampling. So is this going to be the right answer? Turns out it's not exactly the right answer. And so basically because it's not, bridge level scores turn out not to be exactly distortion free.
How does the size of S get in the cardinality?
Why does the second equation hold?
In the first one.
It's sort of a standard property of DPPs. The proof is not complicated, but it's I don't have time to go over that. But it's sort of a curious fact.
What the cardinality of S is, that's what that is.
Sorry?
Regardless of what the cardinality of S, that probability statement, that Is in S is equal to that leverage score, that holds regardless of the cardinality of S.
Well, it affects the cardinality of S, right? So the cardinality of S is a random variable, and the expectation of that is the sum of the marginal probabilities. So that's how you relate these two quantities.
Yeah, I see the expectation. It follows clearly from the probability.
Exactly. All right, so the actual distortion-free distribution we're going to use is this kind of more complicated thing called regularized determinantal point process. So I really don't have time to cover this in detail. Essentially, instead of using determinants of the submatrix, we introduce this identity as a regularization. And we introduce this additional term here, which controls which sort of depends on the subset of the sequence length, which is actually a Poisson probability next to the determinant. And so the theorem just says RDPP, as it's called, is a distortion-free intermediate distribution where the downsampling is done using just a DPP, a property scale.
It doesn't seem like that will be related to leverage scores. Leverage scores don't worry about only one data point at a time, right? So they cannot worry about angles and volumes somehow.
Yes, yes.
But this does.
Exactly, yes.
But then I don't see the relation between those two. But maybe you said there is.
What do you mean? It doesn't worry about all the other data points.
It doesn't worry about.
It's a univariate statistic for each data point that worries about all the data points.
But determinants are
That's right, but you pick according to leverage scores may be high, but they may not be orthogonal, they may be collinear more or less. That is a problem.
Right.
Yeah.
So
Yeah,
this
which is why
exactly.
They're not
marginalization.
determined by eigenvalues, but determinants are determined by eigenvalues.
Right. So you can, yeah, you exactly. So this distribution does address the problem where with leverage scores you might be very unlucky and get points that are sort of collinear.
That are collinear.
Exactly.
Yeah.
So this addresses that problem. All right. So I was going to go over the proof sketch of the last theorem, but I don't think I have time. How much time do you have?
Could you just give the main idea why that thing works?
2 or 3 minutes.
Okay.
So
Just one sentence or so.
Sure, yes. So skip that slide. All right, so okay, so here's the main idea. So we want to show that the intermediate distribution cancels out of the probability. So here's the, okay, so recall we're sampling sigma from the RDPP, we're sampling S from the DPP. And so if you look at the probability of the final subset being equal to T, we can sum over all sigmas, right? And so T given S, T given sigma is the probability of the downsampling, the subsampling DPP. And the second part is the probability of the RDPP. And notice that we designed it exactly so that the probability term, the numerator of the RDPP cancels out with the denominator of the DPP. And those are the only two terms that have sigma in them, which means that after that cancels out, the summation just becomes counting. And it turns out that if you do the counting right, you end up with, everything cancels out properly.
What do you get from the exponentials to the determinant?
What do I get from the exponentials at the end?
R to the t to the minus t over t.
It's a little complicated. Essentially, we're summing over sequences of all sizes for technical reasons, and the determinants kind of behave differently for different sizes, different size matrices. So we have to correct for that with this R to the t. That's all I can do for now. So I refer to the paper, but it's necessary, but it's a sort of a technicality. The key idea is this cancellation.
I think the key idea idea is that remaining term sums up to what you need for me. That r to the t to the minus t over t factorial. Nothing else would have done just this thing.
This is how the weight determines the
This is
size. That seems
so the
like
That's
Poisson.
another way to work.
weight determines the different size. That seems like a key.
So the Poisson distribution, I wouldn't say this is the only thing that would do that trick here necessarily.
Or so you just pick some suitable distribution. I see.
I mean,
Okay.
I will also say that this is the only one that I got to work. So I mean, but I mean,
Okay, fine. Okay.
yeah, the calculation is not very complicated if you expand it. It's just it's longer. All right, so we got two candidates. One of them is distortion-free. One of them is efficient. Neither of them is both. So we just put them together, and in a very simple way, we just take the probability distribution of the IID leverage scores, multiply it by the probability distribution of the RDPPs. There's some minor rescaling going on here. And this is the sort of leverage score rescaled RDPP. So the actual analysis that has to be done happens with respect to this distribution. It would just complicate the proof sketch further to do that. But I mean, so you actually have to use both of those sort of ideas in the algorithm. And so the algorithm. So now you have to sample from this distribution. That's the first step we have to do. So this is the algorithm for sampling from the distribution. So it's really just the 3 lines there. We sample first from the IID leverage scores. Then we correct the distribution of the leverage scores to the regularized determinantal point process by rejection sampling. And we just have to wait until this gets accepted. And then after that, by the distortion-free intermediate sampling property, we just have to downsample all the way to the target subset size, which we can do. And the result is that the final result is that S is sampled according to the correct distribution. So the key thing to worry about here is whether or not this Bernoulli probability is upper bounded by 1. And that is and sort of a non-trivial fact that requires that we did all these things previously, like rescaling by the leverage scores and all these things, and choosing those constants appropriately. So it's certainly not obvious that that this rejection sampling actually does the correct thing, but it does. And fortunately, not only that it's bounded by 1, but also it's lower bounded by a constant. And so the result of this is that we get a time complexity sort of guarantee on this, because the number of those repeat loops that are going to happen is constant. And if you look closely, then the intermediate sample size is basically k squared, right? So we have k squared sample size. Computing the determinants there costs the cube of that. So we get k to the 6th. So that's the poly k for the sampling time. So now, since I'm sort of out of time, I will kind of go past this. But of course, I explained everything so far for exact leverage scores. So now, actually, to get faster preprocessing, I would have to do everything for approximate leverage scores, as is standard practice. The one sort of problem here is we cannot use the like 1/2 approximate leverage scores that people typically get away with. We have to use much more accurate approximations, and that sort of shows up in the time complexities. So so for this we just use like prior standard results on estimating ridge leverage scores from this paper. With the approximation quality epsilon equal 1/k, you end up with these n k to the 6th plus k to the 9th as the preprocessing cost. Actually, the algorithms run much faster than these worst case costs, because in practice, you don't actually need epsilon equal 1/k. In practice, you actually can get away with epsilon equal 1/2. And finally, there's a reduction from DPPs to k-DPPs we proposed. and basically, it says that, well, what is a k-DPP? It is just a DPP for which we restricted ourselves to a particular subset size. So there's an obvious rejection sampling strategy we can do to just pick only the subsets of the right size. And it turns out there is a way to rescale a DPP such that the probability of one particular subset size is order 1 over root k.
Excuse me, I just to get still to the idea, if I were to do that in a brute force deterministic way, I'd either compute the symmetric function, the partition function, or I compute an eigenvalue decomposition and maybe use Cauchy's interlace theorem. Why is that so? Why is this approach so very different? What's the connection there? I'm just trying to understand the idea. For me, it's so foreign, that idea. So I just.
It's yes. This is very different than the previous algorithms for DPP sampling. I'm not sure exactly what is the algorithm you're suggesting, because I mean we have.
I could either brute force compute determinants.
Sure, but that will be exponential time, right? Because there's, I mean, each subset has a different probability, which is a determinant which you have to compute, right? So already the first algorithm that was proposed, which did the eigendecomposition, that was already, a step forward going away from the brute force, right?
Yeah, and then one could use interlacing or something to get, probabilities for smaller, sets.
Well, I'd be interested to hear more details about that.
I'm just wondering why.
Sorry, can I have a quick question? I don't mean to.
Yeah, this is basically over, so I can take questions.
I'm puzzled about one example. Your acceptance probability being not too small. What if you had n over 2 pairs of pairwise collinear things? It seems like you reject a lot, but maybe there must be some reason. I mean, the acceptance probability being big is important, very important, right?
Acceptance probability being big is important, yes, and I can certainly say that if you don't get the parameters just right, the acceptance probability will be exponentially small, very easy.
That seems tricky, yeah.
Yes, yes. But in fact, we are very conservative in the theory, where we are guaranteeing that the acceptance probability is constant, and in fact, in practice, you can be much looser with the parameters to achieve that. All right, so yeah. That's it. Conclusions, I mean, some future directions.
So why don't we call that the question session, just because it's in the interest of time, and get Miles set up. But thanks. Thanks.